This is an introduction to the least square adjustment method of observations. Let's start. Before we start with the method, let's take this example, which is the line equation. Line equation, y equals mx plus b, where y is the y value of a point, x is the x value of the point, m is the slope of the line, b is the y intercept, as you can see in this drawing. This is the y-intercept, and here is the slope. And for any point, the y of the point, for example, a, the y value of a is equal to the x value multiplied by the slope plus the b, which is the y-intercept. Now, if we want to find the equation of the line, on that line, we measure points, and these points we will try to find the equation from those points. What is the minimum number of points that are needed to be measured on the line to be able to find the equation? This equation has two unknowns, m and b, so we have a minimum of 2 points that we need to measure. But what if we measure more than 2 points? A, B, C, and D, for example, 4 points, 5 points, 100 points on the line. So what's going to happen is that if you choose any 2 points, you will get a solution. You will get different values for M and B. So which M and B, which 2 points that you need to pick and then you use for finding M and B, this can be like endless methods. All the points, they are measured and they have the same probability to happen. So there is no, from those points, we have no 2 points that they have like special values or special properties that we say, okay, I would take A and C, or I would take C and B. I would take. So what shall we do? The solution for this is that we will take all of these points, A, B, C, and D, and even if they were 100 points or more or less, then we will go through what we call the least square adjustment, and we will make all the points participate in the solution. So we will get the line that will fit, or it will be optimized by using all the points. So now it's not one or not 2 or these 2 or that 2. We will use all the points, we optimize the solution, and we get the best values for M, which is the slope, and B, the y-intercept, including the participation of all the points. This process is called the least square adjustment method, and this is a method we use in geomatics in general when we have redundancy. Redundancy, that means we have more observations than we have the unknown. So for example, we used to give you this example, which is about the measuring the width of the table. So if you measure the width, you need to measure it 1 time, but if you measure it 2 times, 3 times, 4 times, which one should we take? You should take the, for example, this is the simple solution, you take the average, because the average is the most probable value. It has the highest probability to happen, more than the other measurements which have the same probability to happen. So with this introduction, we can say in geomatics, usually we do measurements to determine unknown quantities. These measurements, we call them observations, and the unknown quantities, we call them the parameters. So we do observations to determine unknown parameters. Now, these observations and parameters, they are related using a mathematical model. If you go back to the line of the line equation, or equation of the line, what do we have? We have y is the y value, observable quantity. This is what we observe. For every x, we observe y. And we have m as the unknown, and b is another unknown. So y is the observation, m is an unknown, and b is another unknown, or they are the parameters. Now, how do we solve using so many points, redundant points that we have measured in the field? We apply this equation for every point. So for every point, we apply this equation, and then we will have so many equations depending on the number of the points that we measure on the line. In the previous example here, we measured 4 points, A, B, C, D. And then we will apply this equation once for C, A, B, C, and D. Now we will have 4 equations. We want to solve from these 4 equations, we want to solve for M and B and get the best value. The best value can be obtained using the least square method, and what we call it, the process is least square adjustment of observation. How is that? It is straightforward. When we are measuring, as we said, we measured 4 points. For every point here, we measured the y for every x. So here is the x, which is xa, and for xa we measured ya, and for xb we measured the yb, and etc. for all of the points. Now, as you can see, that the line that we fit will not go through directly through the points, because we have the random errors. So here it will not be, the line will not go through all the points because of the random errors, and that's why the observation y that we measure, for example, ya for point A, it will have the function, the value that we get from this one. This is the value from the mxi plus b, or mxa, let's say. So this is the value here from the line, and plus this small amount, which is the fluctuation, which is the random error. So we have y that we measure plus the random error will equal to the value of the function for the point x. So we take this equation, we apply it for A, we apply it for B, and for C, for all the points. So we have ya plus the residual at A equals mxa plus B, and then we apply it for B and C and D. So all of these, now all what we have to do is put them in a matrix format. The matrix format, if you can see, L, this is the L. If you call the observations, we call them the L vector, and this is the V vector, which is the vector of the residuals, and this will be equal to this one, the summation here. It can be put in the format of A and X. In our case, it will be XA. The coefficient of M is XA of the first equation, plus the coefficient of B is 1, and then XB, and XC and XD, plus 1, plus 1, plus, sorry, it is plus 1, but it is 1, because we are writing it in a matrix format. So we have 1 here, so we have X and 1, XA and 1, XB and 1, XC and 1, XD and 1, and then this will be the A equation, the A matrix, multiplied by the M and B, the unknowns vector. So let's see. So at the end, now what do we have here? We have the observations, the residuals equals the coefficients, and we call it the A matrix, we call it the design matrix, and X is the vector of the parameters or the vector of the unknowns. So here, again, this is another representation in matrix format. The residual was the observations and the coefficients, and the coefficients of the unknowns. So here A11 will be coefficient of x1, A12 coefficient of x2 in the first equation, and then the same thing for the second equation. Now the observations, M is the number of observations, N is the number of the unknowns. Now, how do we solve using the least squares? Actually, the solution is straightforward. We do not go into the complications of deriving the solution. We will just apply it. Once you have L plus V, the system, we call it the observation equation system, which is LV plus V equals A to AX. How do we start the solution of the least squares? We say N, we call it the normal matrix, equals, you take A, the coefficients, transpose it, and multiply it by A, and then you create another vector called the normal vector, which is the A transpose, the transpose of the A matrix, multiplied now not by A, it is by L, which is the observations vector. Now N multiplied by c equals x, which is the solution. N, wait 1 second. N multiplied by x equals to c. To find the x here, we multiply this equation from the left by n minus 1, which is the inverse of n. N minus 1 multiplied by n multiplied by x equals, to the left we have n, we multiply both sides. So here n minus 1, which is the inverse of n, and the inverse of n. Inverse of n multiplied by n, this is the identity matrix. If you multiply it by unknowns vector, it becomes just the unknowns vector I, the identity matrix. So here it will be n minus 1 multiplied by c, and also at the end it is n inverse of the matrix n multiplied by the vector c. So here is the solution. And if you replace n by A transpose A and the c by A transpose L, at the end, when you take the n, invert it and multiply it by c, you will get that. What are the unknowns here? The unknowns, they are m and b. So that's it, we take m and b. If you want to calculate the residuals vector, all what we have to do is ax minus l. From the equation here, v equals l plus v equals ax, so v equals ax minus l, which is this equation. We will find the residuals, which is a representation of the random errors coming from the measurements inaccuracies. Now, more details. So this is the line equation. We have written all the observation equation system. This is the observation equation system, and we put it in a matrix format. All right. So we continue. Now, for a numerical example, we want to just to replace y. This is the y of 0.1 and the x of 0.1. So here is the ya, so it is 4.5, while x we multiply it by m, and the coefficient of b is 1. The same thing, x for the second equation and y for the second equation, second point. And c, this is x of the point c, and this is the y of point c, and we have 8 and 550 for the 4 point. So the coefficients, they are, this is the a, the coefficients is 3, and 1, 4.25 and 1, 5.5 and 1, and 8 and 1. This is the a matrix multiplied. So this is to the right here, it is the matrix format of this observation equation system. So all what we have to do, and this is what we have, 4.5 and the equations. So we have a and we have l. From a, we find A transpose A, we find C matrix, and A transpose L, we find the C vector, and we calculate the solution for M and B. As you can see here, the solution is that we take, this is A transpose, and this is A, the original A, and this one is A transpose again, and this is the L vector. Do the multiplication, do the inversion, and we will get, and this is the C, and this is X, and this is, this is N, X, and this is C. All what we have to do is invert N and multiply, and multiply N minus 1 into the left and the right. So at the end we will have this equation, inverse, this is N, this is the N matrix, inverted here, multiply it by C, and you will get the unknowns vector. This is M and this is B. How did we know this is M and this is B? Because in the A matrix, we were using, as you can see here, first column, it was about the coefficient of M, and this is the coefficient of B. So that's why we know the first answer here, when we get the vector, the first value is for the M. You can switch them and switch the coefficients, and then B will be the beginning. So it will follow the order that you have used from the beginning. How do we do this solution numerically? We do it using Matlab. In Matlab, And there is a separate video for using Octave online for doing the measurements. Now, adjustment of observation. This is a typical least squares adjustment code for Matlab. So put this in a file. Just you can copy it from the slide and put it in the file in the Octave online and run the software, run the program. So every line that has a percentage and so front, this is a comment line, just a comment. You want to do some documentation inside the program. So you put here, after you put the A, like there is the comment can be a straight one complete line, or it can be a partial line. Once we write something, we can add a comment to the line. So this will be just a comment, and the other part here will not be a comment, like what you see in these. In the clear all, this clears all the memories, memory variables. CLC, it will clear the display window. You will see later, and if you run the Octave, you will see that CLC will create the clear the window. Sometimes you will do one run, and the display window or the results window will be full of values. Then CLC will just clean it. We put the A matrix. The A matrix we have first to add a matrix in MATLAB. You say A equals, very simple syntax when you are using MATLAB. So you open a square bracket, and then the first line 3 and 1. You can put 1 space, 2 spaces, just for you to organize your work. And then you go to the second line, 4 and 1, 5 and 5 and 1, 8 and 1. Then when you finish the equation, you close. You can add comments here after the as many as you need. Then we enter the L vector. It is also L equals, we open the square bracket, 4, 5, and everything. Then when we finish, they will see here, this is a vector, and that's why it is 4 by 1, because we have 4 values, everyone on a separate line, and we have 1 column. You can enter this in one line. You can say L equals, you open the bracket, and 4.5, and you add a semicolon, and then 4.25, and you add a semicolon. So the semicolon, it's a column separator, and you can write all of these on one line, and then you close the. So either this format or this format. I think this format is more like visually representing the real shape of the vector. Once we have A and L, this is A and L, we do the solution. N normal matrix equals A transpose. In Matlab, the transpose, you just put the matrix and you follow it by an apostrophe. So this now is the transpose, multiply it by A, just regular multiplication. So that's why we use Matlab. It's very straightforward. And then X equals inverse of N. This is how you invert the matrix n to the power -1, which is the inverse of the matrix. This is how you do it in Matlab. You do inverse of n, then multiply it by c, calculate v equals a star x minus l. X, we just calculated that. L is already there, a is already there, so we can calculate v. Let's look at the this is what you would see in the results window. We put the values in n, and then the values of n, they will be displayed in the window. And C also, it will be displayed in the window, calculation of X and calculation of V. Now, in case you do not want N and C values to show, so what we usually do is that we follow, we follow the declaration of A and N, whatever we want to do, like N here. I don't want to show, now it is there, so I don't want to show it. You just follow it by a semicolon. The semicolon will not make the values, once N is calculated and C and the value, they will not be showed on the output screen. And it looks like in the program that I implemented, the A and the L, they have semicolons, because the A and L, they are not showing here. So it's your choice what you want to see, what you want to hide. Now, this is an introduction to least squares. I will have a separate videos for adjustment of leveling networks. The previous example was introduction, and it was applied, this introduction, to line or equation of the line, and how we assemble the L, and the mathematical model, write the equation for every point, and at the end solve for the B, M, and B, and find the residuals. For this leveling networks, which is essential to this chapter is vertical control. So the equation and the example of the line, it was just for an introduction. Here it comes the application of least squares for this chapter, which is the leveling networks. We'll talk about it in the next video.